Okay, so we are in chapter 6.2, which is conservation of momentum. And we're going to start off the chapter with two situations. We have the situation of two spheres colliding with each other. Sphere of mass 1, sphere of mass 2. Of course, they're different sizes. They may also be different masses. They just tell us their mass 1 and mass 2. We don't really care what their masses are, except that we're going to use those to calculate momentum. In this case, one of them is colliding with the other. We don't really care which one is doing the colliding, and which one is the standstill ball. It doesn't really matter either. But we do know that there's going to be the reaction force due to Newton's third law. One ball on the other and the other ball on the one ball, right? We know that those forces are going to exist. And here they have those forces labeled for us. This would be the force of ball 1 on 2. This would be the force of ball 2 on ball 1. And you can see here that this collision, since these are spheres, we get linear momentum that is collinear. What does collinear mean? Collinear means that these momentums are both along the same line, so it is truly one-dimensional. And the beauty of that is that it makes the conservation of momentum a very easy thing to talk about, a very easy thing to calculate. And so how do we do that? Well, to talk about conservation of momentum, first of all, we have to calculate momentum. Momentum is force times mass, mass times velocity. And in the case of these two balls, we maybe had, let's say that we had the first ball, M1, moving towards M2 to start with, and it would be moving along this same line, this collinear line, and it strikes mass 2, and then mass 2, after the collision, is going to have some velocity, mass 1 is going to have some velocity, and when they hit dead on like this, one ball hitting the other ball, without any glancing angle, in other words, the velocity is in the same direction that passes through both of the centers of these balls, then what we get is a conservation of momentum that is completely in one dimension. And all we have to really do is think about the signs of the momentum. So if mass 1 was moving to the right, we'll call that positive, so it is a positive momentum to start. If mass 2 was sitting still to begin with, then it will be moving to the right after it gets hit by mass 1, and so it will have a positive momentum. But mass 1 may bounce backwards and go the other way, which means it might have a negative momentum to end up. Well, what really matters here in the end is that at the beginning of the problem, before the collision or before the interaction, there is a total momentum in the system. Maybe ball 1 has this positive momentum we talked about. Maybe ball 2 is zero momentum, or maybe it's moving as well. It doesn't matter. But if we take all the momentums that we start with and add them up at the beginning, and then after the collision or after the interaction, we add up all the momentums, it should be the same exact momentum. Now, there is one caveat here. Momentum is conserved all the time. However, it's not always obvious where it's conserved. And so we like to do these things in the absence of non-conservative forces, because when you have non-conservative forces involved, like friction and things like that, those non-conservative forces they transfer momentum into things outside of our system. For example, they transfer momentum to the Earth, and they transfer momentum to the air. The momentum gets transferred somewhere else, and it's still conserved, but it's very difficult to keep track of. Very similar to the conservation of energy situation. Sometimes it's difficult to keep track of that energy. But as far as we have observed in physics, momentum is always conserved, and we actually have some really compelling observations been made in recent years that momentum is conserved. And that's kind of a subject for the second semester of this class, but the reason I say it's compelling is that they actually show that momentum is conserved even when we talk about light interacting with matter. And so that's a very interesting subject to get into in the second semester of this class if you have to take it eventually. You can also have conservation of momentum without a collision, but with just an interaction. In this case, we have a proton, this P positive here, and we have a helium ion, which is just essentially two protons stuck together with a couple of neutrons holding them together. but you get this proton and this, what is called an alpha particle, this helium ion, and they pass close to each other and they repel each other. And this proton coming in on the left has a momentum that is in the direction of its original motion times the mass of that proton. And the helium ion coming in from the right, going towards the left, has another momentum that is in the opposite direction, but it's going to have a different value, different mass, different velocity. And so when you get these two momentums to begin with, instead of colliding, they actually just interact through this electromagnetic force that repels them, like charges repel each other, and they veer off in different directions. But if you calculate the momentum later, this will be a different momentum upward and to the right instead of just to the right. This will be a different momentum downward and to the left. But it turns out that the upward momentum of this particle and the downward momentum of this particle will actually cancel out, so that you only have left and right momentum. In fact, you can have a total of 0 momentum in the system if these two momentums are equal and opposite to begin, and at the end they will have equal and opposite momentums as well. So, conservation of momentum between colliding particles and interacting particles. As far as we know, it is always observed. There's always this conservation of momentum observed between masses passing in the night. Also works with things that aren't masses, but that's again a topic for the second semester of this course. So here's another example of this. This one is in an active figure, so it's kind of nice. So we have our initial position of each of these particles, and we can actually set the initial velocity of each of these particles. So the velocity of ball 1 is going to be, looks like 10 meters per second. Initial velocity of ball 2 is going to be 0. And then the mass of ball 1 is 5, mass of ball 2 is 5. And we're going to go ahead and start this thing and see what happens to the final velocity. So the first one starts, bounces, and then so what happens here is the velocity initially of ball 1 was 10, and ball 2 was 0, and they essentially switched in the final velocities. We have ball 1 is 0 now, and ball 2 is 10. And what happened is that ball 1 transferred all of its momentum into ball 2. And why did it do that? Well, the reason is because ball 2 had 0 momentum, and ball 1 had all the other momentum. And they hit each other kind of head-on, so that there wasn't a bouncing off at an angle effect. We call that a glancing angle effect. And also that they had the same mass. Because they had the same mass, the momentum transferred evenly through the velocity. In other words, the velocity was the same in the second ball as it was in the first ball. So what would happen if you increase the mass of ball 2? Instead of at 5, it's at, say, 10. Mass of ball 2 is 10. We're still going to come in directly head-on, so it doesn't turn the ball any. But what happens, though? We have these two balls, we have 10 meters per second again. But notice that the small ball, instead of just hitting and stopping, it bounces off and goes backward. And the bigger ball gets most of the velocity. In fact, since we have a total mass of 15, and ball 2 has 2/3 of that mass, ball 2 gets 2/3 of the momentum. Or sorry, 2/3 of the, gets 2/3 of the velocity. So it's 6.67 for the ball 2. And ball 1 only gets 1/3 of it because it's only 1/3 of the mass, and it's actually in the opposite direction. But it turns out that the total momentum to begin with was the same as the total momentum to end. And we'll see how that works working out in the math a little bit later. Let's go ahead and increase the mass of ball 1 up to 20. So now ball 1 is 20, ball 2 is 10. And ball 1 is going to come in with this velocity again of 10, and we're going to see what happens. So ball 1 comes in. And you can see here that ball 1 keeps going, but it slows way down. So ball 1, we have this interesting thing going on again, where we have the mass of ball 1 is 20 and the mass of ball 2 is 10, so it's 2 times as much in ball 1 as in ball 2. And in the end, ball 2 ends up going quite a bit faster, actually. Takes off really well, takes most of that velocity away from ball 1, and ball 1 just kind of keeps motoring along. Right? So, other situations that can happen is that the balls can be moving towards each other, they can be moving away from each other, but in the end, the momentum will always be conserved. It's easier to talk about this using math, So we'll get to that. Let's say they're both moving in the same direction. One's just moving faster than the other one. We'll move this one up to 20. We'll start it. So they don't collide in our view here. Let's try it again. So there we go. So they're both moving to the right, and they're both moving to the right. We're going to have moving in opposite directions. Yep. This blue ball is still moving, just very slightly. So conservation momentum is this idea that you calculate all the momentums of all the particles in your system to begin with, add them all together, and again, these are vectors. We have momentum as a vector, so you have to add them together as vectors, and then you calculate all the momentums at the end as vectors, and then add them as vectors, and those two things should be equal. If you don't know one of the momentums at the beginning or the end, or one of the velocities at the beginning or end, then you can use this idea to actually calculate the unknown. So here's the equation you end up with, the conservation of energy equation. Mass 1, V1 initial. Notice the V is a vector. Mass 2, V2 initial equals mass 1, V1 final plus mass 2, V2 final. And you can extend this to as many different particles as you want. So let's take a look at excuse me. This is actually a really good example here, the squid's propulsion system. How does a squid or an octopus take off? This is particularly true. It's more true of squids, but octopuses also use this method a little bit. But essentially what happens is a squid fills up this cavity up here, which is just a big muscle and a cavity for holding water. They fill that up with water, and then they squirt it out really fast backwards, and then they go forward. Why is this an illustration of conservation of momentum? Well, it's quite simple. At the beginning, before the squid does anything with these muscles up here, the water that's inside the squid is not moving. The squid itself is not moving. Let's say that it starts from rest. And so the total momentum of the system is zero, because nothing's moving. The mass is all just sitting still. But then it contracts these muscles up in here and squirts that water out backwards. Well, now the water has backwards momentum. And the total system has backwards momentum, even though when you started you had zero momentum. And so to cancel that out, or to conserve that momentum, the squid has to move forward. And that's exactly what happens. As the water moves backwards, the squid moves forward. And that's true of rockets and jet airplanes and many other systems that use this idea of propulsion by accelerating one object or accelerating one mass, usually some kind of gas or liquid, and causing the other mass in the system to accelerate in the opposite direction. So let's do an example really quick, and let's see this in action. We have an archer here. Of course, the archer is not going anywhere. The arrow is not going anywhere. The bow is not going anywhere. So the total momentum of the system is zero. No velocity anywhere. And here they give us some mass. His total mass, including his bow and quiver or arrow, is 60 kilograms. He's not a very heavy person. If the archer fires a 0.030 kilogram arrow horizontally at 50 meters per second, in the positive x direction, what is his subsequent velocity across the ice? So he's standing on frictionless ice. They want to know what's going to happen if he fires this arrow in one direction. Is he going to move backwards in the other direction? Well, he should. How fast is he going to move is the question. So we use our momentum equation, which says that the initial momentum has to equal the final momentum. And since it's only in one dimension, we don't have to worry about vectors, but we do need to worry about the signs of the velocities, so that we'll say to the right is positive and to the left is negative, for example. The initial momentums, of course, are zero because nothing's moving. The final momentums are the mass of the man times his final velocity, plus the mass of the arrow times the final velocity. Actually, I think the arrow is mass 1. So mass of the arrow, which is m1, times velocity of the arrow, plus mass of the man times velocity of the man. And we know the mass of the arrow, we know the mass of the man, we know the velocity of the arrow. The only thing we don't know is the velocity of the man, which is v2f, or v1f rather. So we're going to solve for this equation for v1f. We solve this equation, we get negative mass 2 over mass 1 times v2f, and we plug in our numbers, and it turns out that we do get a negative velocity for the man of 0.025 meters per second. Does this make sense? Well, the velocity of the arrow was 50 meters per second to the right, but it had a very small mass. So 50 times a small number, and then on the other side, on the other part of this, we have the man going backwards, but he's going backwards very slowly, but he's also very massive. So he has a big mass going slow equals a small mass going fast. Or, and in this equation, you're actually adding those two together to make them equal to 0. And so you add the mass times velocity of the arrow, which is small mass times big velocity, plus big mass of the archer times small velocity, but the small velocity is also negative. So you end up with a number minus a number equals 0, and that's true. So this makes sense to have a very small velocity for the man. And you would expect that anyway if you've ever shot a bow and arrow. You'd know that the bow and arrow doesn't have much kick. It doesn't kick you backwards very much. But it does kick you backwards some, even if you don't realize it. Now with a gun, it's much more obvious. With a gun, you can feel the gun kicking backward and pushing you backward as the bullet goes forward. And the bullet moves so much faster out of the gun that the kick is much bigger, much more noticeable. And for guns that shoot bigger bullets, the kick is usually bigger, but not always. And people kind of wonder at that. For example, if you're shooting a .30 caliber lightweight hunting rifle, which many hunters use because they're lightweight and you can put them on your back and you hike into the woods, a .30 caliber hunting rifle has a bullet that is much smaller than a 50 caliber rifle, a 50 caliber black powder musket, for example, which shoots a huge ball of lead. But the big black powder musket doesn't kick very much for a couple of different reasons. First of all, it doesn't accelerate the bullet as fast as the rifle does, so the velocity is down. But also, a black powder rifle is generally quite a bit heavier than your average hunting rifle, usually about 10 times as heavy. They're very heavy, and so they add a lot of weight to the hunter. And so to push the hunter and that big old barreled gun back is kind of difficult. It takes a huge amount of momentum change in the ball. And there just isn't enough change there for it to kick too hard. In the second part, we're going to calculate the archer's velocity after firing the second arrow. But this time he's going to fire that arrow at 30 degrees above the horizontal. So not all of his arrow's momentum is going to be horizontal. Some of it's going to be vertical. So we're going to have to deal with some vectors here. In particular, we're going to have to multiply the velocity of our arrow times the cosine of theta. And if you're not sure why that's true, well, let's take a look here. We'll go to Educreations really quick. I guess I'm going to remember to do that, so we'll just go to the next page. So anyway, if the archer, here's our archer standing here. How come it's not letting me draw? Oh, because I'm not on draw. Here we go. Now I'm on draw. So if our archer is standing here and shoots the arrow horizontally, then of course the archer moves horizontally with the same but opposite sign momentum. However, if the archer shoots his bow up at an angle, so now his arm's up this way, and he shoots his arrow up here at this 30-degree angle, now, all we're interested in, let's write that in, 30 degrees, all we're interested in is the component of this vector that is in the x direction, because that's the only direction the person can move. If you try to move the person down, you got this sheet of ice in the way that will stop him from moving. But we need this component right here, and since it is adjacent to the 30-degree angle, and this up here is our, let's say this is our velocity to final, after we've shot the arrow, then the thing that we're interested in, which is right here, is going to be velocity to final times the cosine, because it is the adjacent angle, of 30 degrees. So that is how they do that, and you can see here that in the example, they have that cosine written right into velocity 2. Velocity, mass 1, velocity 1 is the initial velocity and mass that we've got. And that's because after he shot the first arrow, he's sliding backwards some. It's frictionless ice, so he's still sliding. Then he turns, so we've got the mass of the man and the velocity initial of the man. The velocity initial of the man is this number we calculated in part A. So we plug that in down there. And then the second one is going to be mass 1 minus mass 2, because remember, that's the final velocity of him after he's shot the arrow. Plus mass times 2, velocity 2 cosine theta, which is the velocity and magnitude of, the momentum of the arrow the second time. Cosine theta has got to be it. So now we end up solving this for V1F, which we don't know, and we plug in all the stuff we do know: mass 1, mass 2, velocity 1 initial, velocity 1, let's see, velocity 2 initial, and velocity 2 final are the things that we know. So we solve that in this cases, and then we're solving for velocity 1 final, and we've got everything we need: mass 1, mass 2, velocity 1, velocity 2 final, and cosine of 30 degrees. Plug it all in and we're good to go. The third thing they have us do is to estimate the average normal force acting on the archer as the arrow is accelerated by the bowstring. Remember, normal force can be measured different ways. You can use an equation like this, where you take the initial and final velocity squared, take the difference, equals 2a delta x. That's a kinematic equation. Hold on just a second. So that's a kinematic equation from chapter 4. And, chapter 4. So you can use that equation to calculate the acceleration. And once you've got the acceleration, then you multiply that by the mass and you get force. And that's exactly what they do here. They also want to know the time. We're going to need to know the time that it takes. And to calculate the time, they use the initial and final velocities again over acceleration. So it's a different kinematic equation. And then they want us to write the y component of the impulse momentum theorem. Well, in this particular case, we have this 30-degree angle, and so we're going to end up with a sine of that in there because we want the y component of that. And we calculate that using the same kind of methods we used up above, same stuff. So you can see the momentum being a vector. There's a little bit more complexity involved. And we will get plenty of practice doing this. We're moving on to section 6.3, and I'm going to stop this recording and start again. Actually, I'm not going to stop this recording because we have to go look at a homework assignment. Let's go look at a homework assignment. So let's take a look at homework 6.2. And I have given 4 problems. We have a high-speed stroboscope, which is just a strobe light. They take some photographs, so they have stroboscope photographs, and they show the head of a 270-gram golf club traveling at 41 meters per second. So the fact that they've taken pictures of this doesn't matter. They're giving us the stuff we need: the mass of one thing, the initial speed of one thing, and the mass of the second thing, and the initial speed of the second thing. The golf ball is 0. And after the collision, the club head is going to have a different speed. So they've told us the final speed of that. They want us to calculate the final speed of the golf ball. It's just a conservation momentum equation. Number 2, a very similar thing, except it's a rifle firing a bullet. The interesting thing is that the recoil that a person feels from shooting a gun will be the same recoil that the person feels, or an object will feel, if it receives the bullet. In other words, if they get shot, or the item gets shot. And so in the movies where they show somebody getting shot by a handgun and they get flown off their feet and go flying back 5 feet and slam up against a wall, it just doesn't happen. Think of, if you've ever shot a handgun, think of shooting a handgun. That's exactly how much force you would feel, and for about the same amount of time. Now, there are other bad effects to being shot. It may shoot you in a place that you bleed to death. It may shoot you in a place that will stop your life instantly. It may just shoot you someplace, and that's just not pleasant. But the point is that the movies, of course, don't take into account that the conservation of momentum has to be conserved, and it certainly is. Let's see, a girl of mass mg is standing on a plank of mass mp, both in relation to rest on a frozen lake, so this is similar to the shooting the arrow on a lake. And there's originally a rest. The total momentum of the system initially is 0. And so it's very much like firing the arrow for the first time on the lake. We're going to push the block in one direction, and the girl's going to go sliding in the other direction. Conservation of momentum. But all the initial stuff is equal to 0. Here we have a 78 kilogram fisherman in a 132 kilogram boat. Throws a package of this mass horizontally towards the right with a speed of 4.8, neglecting water resistance and assuming the boat is at rest before the package is thrown, and finding the velocity of the boat after the package is thrown. Again, that's going to be conservation momentum where at the beginning everything is at 0 and then he throws the ball, and so you're going to get most of your momentum going in the ball, but some momentum in the boat going the opposite direction. Just set up all your initial momentums, set them all equal to your final momentums, and you're good in all these problems. So now I'm going to stop this recording, and I'll move on to another recording for the next section.